haven't been there some time ago, Sila mentioned that we'll have a slight change in program, or we are going to reshuffle the sessions a bit. So Istvan, he's now for Professor Legari, he's going to present MRI, and then you'll run directly afterwards the practice, as far as I understand. And then it's then Sila, you will present, no? You're muted still, okay.
Yes. Hello, everybody. Today presenter is István Homoya. He is a PhD student of David Legradi, and his topic is MRI. First, he will show you the presentation about the basics of MRI, and after that, for the laboratory work. Thank you.
Okay, and then you will talk, and then we make a break, and then there will be the presentation and the lab on CyberLife after the break. Okay, so let's go through the last meters of our marathon this week, and I'll hand over to Istvan. The floor is yours. You're still muted, Istvan. Oh, no, something is with your microphone. We can test this.
Can you hear me now?
Now we can hear you, yeah.
All right. So, hello, everybody. Today I'm going to give you a presentation on MRI physics. I've prepared a pre-recorded version of my presentation, so I'm going to share the screen and play the video, but I will be present the whole time. And once the theoretical part is over, I will show you another video about the lab exercise that was prepared. And after there will be some time for questions, and I will be eager to answer all of your questions. So let me share my screen and start the video. All right. So I hope you can see.
Yes, we can see you.
All right, so enjoy.
But the tone is very bad. The transmission is very bad here.
Is it?
Yeah, at least for me. I guess maybe everybody else can give me feedback, but can you try again? But I see it's very pixelized. No, it's very bad. It's very bad. Istvan, can you run the presentation live now? No, we cannot hear you.
Yes, I can run the presentation, of course. All right, just a moment. I open the slides and I will be ready. Okay, so can you see my presentation? Can you hear me clearly?
Yes, perfect.
Perfect. So, okay, I restart everything. All right.
Okay.
So, great. So, hello, everybody. My name is István Homoya, and I am a PhD student of David Legradi, and I work in the Institute of Nuclear Techniques at the Budapest University of Economics in Hungary. And my PhD topic is magnetic resonance in general. So today I'm going to be talking about the theoretical principles of magnetic resonance imaging, how we start from the beginning and how we get to the point to get a full, complete image at the end. All right, so let me show you some examples regarding the MRI images. This is only one modality, but as you can see, you can make an image plenty of body parts, and also you can define plenty of contrast. Just take a look at the images of the brain. Sometimes the gray matter or the white matter is brighter, or instead of showing the tissue itself, we can have a clear picture of the vein system in the human brain. So this powerful tool, MRI, is capable of defining plenty of contrast. And my goal today is to give you the very basic principle of how an image is created and how we can get to these images, how we can create spatial encoding. All right, so let me start at the very beginning. I'm going to build up the bricks of imaging one by one. First, it may seem a little bit distant, but believe me, it will be all necessary to have the rough idea how an image is created. Okay, so what are the advantages and disadvantages of an MRI scanner? Because there are some. The great advantages of an MRI scanner and the whole technique is that there is no ionizing radiation at all. So an MRI experiment can be performed as many times as it's necessary. There will be no health damage at all. It has a considerably better soft tissue contrast, for example, compared to computed tomography CT. And not only MRI is capable of creating anatomical images, but also functional and diffusion scans are obtainable. This is a very, very powerful tool, especially in research and advanced medical and clinical application. However, there are numerous disadvantages as well, such as there is no tolerance at all for ferromagnetic materials. So let's just think it over. If you get injured in a car crash and you lose your consciousness, you will not be put into an MRI scanner because the medical staff do not know whether you have any implants or pacemaker or anything ferromagnetic in your body. They will make a CT examination instead. So even though it's very powerful and it's a very good tool, it's not always replaceable, or CTNet cannot always be replaced with MRI. And also the other disadvantage is that it's loud, so there is an acoustic noise going on, and also the long data acquisition. Great part of the MRI research is focused on shortening data acquisition. All right, so this was just a rough overview, and let me guide you through a short historical overview of MRI. Here you can see the images of two gentlemen, Enver Purcell and Felix Bloch, and they were the ones who came up with the principle of nuclear magnetic resonance, or NMR shortly. They realized that if you place some nuclei into a magnetic field, they can absorb energy of a given frequency. Shortly after, only 6 years after, they were awarded a Nobel Prize of Physics. So just let me emphasize how short amount of time that is in research and in general for being awarded a Nobel Prize. All right, so it was a great discovery. And also here on the slide, let me just break down what is NMR and how it refers to the phenomenon that we are going to discuss today. So the first is, it means that nuclear. It means that it's a feature of a nucleus, so the very center of the atom. After, it's going to be magnetic. What does it refer to? So the whole phenomenon that we are discussing is only transmitted in the presence of an external magnetic field. So in everyday environment, this does not happen. And the last part is the resonance part. It means that we really need a very narrow bandwidth of electromagnetic field that can be absorbed by the nucleus. Okay. Moving forward, you can see with the historical overview that the first NMR scanners and the first medical applications were pretty rough. I mean, comparing this thorax image to the ones that I was showing you at the very first slide, it's clearly visible how much the technology advanced. But let me tell you that the physical principles are still the same. Just the technological evolution has accelerated a lot. Here are some dates when the first clinical scanner was patented in 1977. So if you think it through, this whole technology and MRI as a scanner and medical tool is a very, very young and fresh and highly researched area. All right, and just to highlight it, Paul Lauterbur and Sir Peter Mansfield were awarded a Nobel Prize of Physics for suggesting nuclear magnetic resonance as an imaging tool and creating images. So there are two blocks of Nobel Prizes connected to this technology for the discovery of the phenomenon and after creating a medical scanner out of it. Okay, and just one last thing on this slide. What's the difference between NMR and MRI? So NMR stands for nuclear magnetic resonance, and it means that there is no spatial encoding involved. So it's basically a spectroscopy. Whereas for magnetic resonance imaging, it means that there's a spatial encoding. So we are going to be able to connect some physical quantity to the spatial location, create an actual image. All right. And here you can see also some images from the first Philips scanner. You can see that in 30, 40 years, how much the technology advanced, and the same head scan for a Siemens scanner. All right, so let me help you put together all the pieces that we need. So what happens when we would like to do some measurements? So the first thing that we need to do is put a magnetic moment into an external field, because on the left you can see without an external magnetic field, all the magnetic moments point into random direction. It means that there will be no macroscopic external magnetic field generated. Whereas if we apply an external magnetic field, a pretty strong one on the right, you can see that they will all align parallel or anti-parallel, it depends, to the external magnetic field. It means that all these magnetic moments will create supplementary external magnetic field on their own. And this is what we can modify, this is what we can measure, this creates the interaction with the imaging tool. But it's not as simple as that, because these spins do not just align parallel or anti-parallel to the magnetic field, but they do a special dynamic motion. It's called the precession. Because all these magnetic moments, all these nuclei are particles, they have an intrinsic angular momentum. It's called the spin. And if you place a spin into an external magnetic field, there will be a net torque effected on this spin. It's going to create this special precessing movement, this special precession. So on the right, you can see how this precession, how these dynamics actually work. So there is an axis, the axis of the applied magnetic field, and all around it, the nucleus is spinning all around on an orbit. This is called Larmor precession. This is the very name. And as this is a precession, there's a characteristic quantity that needs to be defined. This is the frequency, the Larmor frequency that defines the precession. The Larmor frequency, omega L, can be calculated as the gyromagnetic ratio, and B, the product with B, this is the external magnetic field. All right. On the slide, I give you a few examples how you can calculate the Larmor frequency for a given nucleus in two external magnetic fields. I define the gyromagnetic ratio for proton here because in a medical scanner, in human medical imaging, we measure the signal coming from protons in a water environment. So this is the very relevant quantity that we would like to define. So here you can see that it's a simple product that we need to take, and we can calculate that at 3 Teslas, the Larmor frequency, the precession frequency of these spins is 128 megahertz, and also same for a 7 Tesla scanner, which leaves us 300 megahertz. It's a very, very fast movement. So the precession that you can see here is pretty slow. So all the magnetic moments precess very, very fast all around the external magnetic field. So you need to imagine that there is a new thermal equilibrium, a new equilibrium when we put magnetic moments into an external magnetic field. They will not be standing, but they will be dynamically precessing, but this will be their equilibrium state at the very moment. And how do we measure this signal? This is a very important part of the whole MRI scanner build-up. It's very simple. We use induction. So the MRI signal is created due to the precession of these magnetic moments, and they induce a current in a conducting loop that is placed around them. So on the right, you can see that there is a loop in the magnetic field, and this magnetic field changes due to the Larmor precession. There will be some current induced in the loop, and we can measure this alternating current in the loop. So this is Faraday's induction law. There is no specific part for MRI, but this is the very physical principle that we use for detection. All right, moving on to the next part. We need to take into account the interaction of the external field with the magnetic moments. As I told you, this precession around the external magnetic field is the new equilibrium state. But what happens if somehow these magnetic moments are not in this equilibrium state? Well, they will be relaxing, and these relaxation procedures are happen as follows. So if they are not parallel to the external magnetic field, they will reach this equilibrium value by realigning the external field with this precession movement. And you can see two processes, two parallel processes going on. Transverse magnetization that is relaxing, and the longitudinal magnetization that is relaxing. You can see the two equations written here, and also I plotted how they seem as a function of time. These are purely exponential decays. So the transverse magnetization that is perpendicular to the external magnetic field will decay exponentially, whereas the longitudinal magnetization will also decay, but parallelly the equilibrium value will build up and reach the equilibrium value. So it's very simple as that. What you need to really remember is that these are two parallel procedures going on. All right, so let's move on to the point where we actually interact with the magnetic magnetic moments. So what we said is, up until a point, they are in perfect equilibrium and they are precessing with the Larmor frequency. But as they are in equilibrium state, we cannot measure any signal. We need to tip them out of this equilibrium state to another state. This means that we need to create a perpendicular component to the external magnetic field. So here you can see on this on the slide that the B0 is the external magnetic field pointing to the Z direction, and we need to tip the magnetization from this parallel state into the transverse plane somehow, which is defined by the X and Y plane. That's the transverse plane. And what do we do? Well, it's very simple. The same thing that we have that we've been discussing previously. We need to resonate with these magnetic moments at their Larmor frequency, and we need to irradiate them with electromagnetic field at a very narrow bandwidth around the Larmor frequency. This procedure is called excitation. So as you can see, the first point is that we turn on an alternating radio frequency electromagnetic field at the Larmor frequency, and thus the spins will absorb this radiated energy. And the stronger radio frequency field is turned on, and the longer we let it affect the whole system, the bigger the flip angle will be. It means the more transverse components will be created in the transverse plane. All right, so this is as simple as that. It's very important in general in MRI to exactly know the Larmor frequency of the magnetic moments, because that will help us to determine what exactly is the amount of energy needed, what's the narrow bandwidth around the Larmor frequency that we would like to capture to irradiate the protons. So in shortly, to excite and to be able to measure the signal in general. All right, so we have come to the point when we are able to perform an actual NMR experiment. The simplest NMR experiment is called the free induction decay. It means that we start from the equilibrium magnetization, we perform an excitation with the radio frequency alternating field, then we tip some of the magnetization into the transverse plane, and then we wait some time and then start the acquisition. What we acquire is this decay curve, this exponential decay curve. So the transverse magnetization will decay as you remember from the relaxation slide. So this is as simple as that. It's basically what we do is we boost the whole system and wait for the system's response. And this response is an exponential decay. The energy that we put into the system is absorbed, and when we leave it alone, the energy is irradiated exponentially, and then the equilibrium state will be recovered. All right, but what you need to know is that these characteristics, so the characteristics of the exponential function is not a T2 relaxation, but a T2 star relaxation characteristic constant. T2 star relaxation time is a superimposed mutual effect of the T2 relaxation and the external magnetic field inhomogeneity. All right, so we can see that. So what does it mean when the external magnetic field is inhomogeneous? So far, we've made the assumption that the external magnetic field is completely homogeneous. But what if it's not? Well, let's make short brainstorming here. But if the external magnetic field is not completely homogeneous, it means that the Larmor frequency will be different position by position. So there will be a spatial distribution of the Larmor frequency as the function of position, obviously. And when we tip all the spins from the B0 direction into the transverse plane, there will be some decoherence at a given time of the small magnetic moments, because the vector sum of these small magnetic moments actually sum up and they give the macroscopic magnetization that we are able to measure. But if we wait long enough, this decoherence will be even greater. And even though there is still transverse magnetization in the transverse plane, here you can see it, there are still vectors going on, the vector sum has decreased, has dropped significantly. It means that there is still transverse magnetization component left, but we just cannot measure it because the macroscopic vector has completely gone away. So what can we do? How can we recover the signal? Are we able to recover a signal? The answer is yes. And here we come to the next very useful imaging tool. It's called the spin echo. This serves to eliminate the T2 star relaxation. Let me define you here what a pulse sequence is. In MRI tool, the pulse sequence is a measurement instruction in graphical forms. So as I told you, as you can see in the graphics or in the small video, we can denote the excitation and the refocusing pulse. So it's very easy to graphically imagine how measurement setup can take place. It's much easier to work with it. All right, so let's take a look how this T2 star relaxation is eliminated with the spin echo. First, what we do is that we perform an FID, a free induction decay experiment. So we excite with a 90-degree pulse, and then we wait some time. But instead of starting the data acquisition at that very moment, we apply another radio frequency pulse, the so-called refocusing pulse. What it's going to create is that the you can see at this, figure C that when all these decoherent state has already been reached, this 180 pulse will flip them. So it's a complete axis rotation. That's how you can imagine, or time reversal, if you'd like to imagine that way. So what happens after the 190-degree pulse? The decoherence will start to decrease. And it decreases, and after the same amount of time, an echo will be formed. So instead of being forced to do the measurement very fast, we can wait some time, apply another pulse, create this echo, reverse the time of this decoherence, and generate an echo. We have much more time to actually switch on and off the hardware system, and also it's beneficial because the T2 star relaxation is eliminated. Yes. And please note that even though the T2 star relaxation is reversible, the T1 and the T2 relaxations are not reversible, they are irreversible. So they contain physical loss of information. If these relaxation procedures start to take place, they will not be recovered by pulse sequences. We need to wait some time so that all the spins go back to equilibrium, and then we can restart the measurement. Whereas for this T2 star relaxation, it's completely reversible with this spin echo technique. All right. And I also hope that this generated video helps you understand better how and when flipping, refocusing, and the echo. All right. So up until this point, I haven't been talking about spatial encoding. So this part has mainly been nuclear magnetic resonance, or NMR in short. So how do we achieve spatial encoding and imaging with this tool in general? The principle is very simple. It's very simple. What we need to find is a physical quantity that encodes spatial location. So if we have this connection, its proportionality, then we're good. Imaging can be performed. So let's see what is that physical quantity. Well, it's going to be the Larmor frequency, because you remember that the Larmor frequency, thus the induced current, is proportional to the external magnetic field. If all spins have the exact same Larmor frequency in a perfect homogeneous external magnetic field, then there is not much to measure. It's going to be a spectroscopy. However, and here comes the principle of imaging, if the external magnetic field is a linear function of the position, then so is the Larmor frequency of individual spins. Thus, one can deduct spatial information from the frequency spectrum of the measured signal. So if we lock together the external magnetic field with a linear function, it will appear in the Larmor frequency. And we know that the Larmor frequency, the precession with the Larmor frequency induces the current in the measurement system. And here we are. If we are able to scale back the frequency spectrum, we will be able to connect the spatial location. All right. One last note here. The linear magnetic field is created with gradient coils, and this magnetic field is called in MRI literature gradient field. All right, so you know the principle. Let's see how it actually works. I will guide you through one more time with this special example on the right-hand side of the slide. This methodology is called frequency encoding because due to deployed linear gradient field during the data acquisition, different spins of the different position will emit an array field with different frequencies. So we will be able to locate them. Okay, let me break it down one by one. So we have a whole sample here. This is the whole imaging volume, and we have two samples at different spatial locations. And we play linear readout gradient field all along the measurement. So this cube, this sample, experiences a different component of the magnetic field than this other one. And then what happens? While they are excited, they absorb the energy and they emit energy via the precession. So they will be precessing with different Larmor frequencies because they experience different magnetic fields. And they will emit these two radiomagnetic signals. But we do not measure them separately. We measure them as the summation signal. We detect this strange summation signal. What we need to do is that we need to take the spectral decomposition of this summed up signal to be able to say from which frequency component we have a lot or we don't have a lot. And for this tool, we have the Fourier transform, which is a mathematical tool. This is able to return the spectrum, the frequency spectrum of a given signal. And what we will see is that spatial locations do not contain any signal, so the frequency component of the space creates zero magnitude frequency component, whereas the two locations of the samples is connected with a high magnitude of frequency component in the spectrum. As simple as that. By playing a linear gradient field throughout the measurement, we encoded the spatial location of the samples thanks to the linear connection between the magnetic field and the Larmor frequency. As simple as that. But in order to have a two-dimensional image, which human perception can process easily, we need another gradient. This is called the phase encoding gradient. What does it mean? So in order to have a two-dimensional image, we need to create a two-dimensional spatial encoding of the linear magnetic field, obviously. In general, if we have an n-dimensional imaging tool, we need n linear gradient field for encoding. So for a two-dimensional image, we need these two gradients. And with phase encoding gradient, after excitation, but before data acquisition, the phase of the spins of different position is modified by another linear gradient field. And this will create perpendicular to the frequency encoding gradient and other spatial distribution of spins. And after, with the phase encoding that we have been talking about so far, can be created, and measuring all these signals one by one, we can have the two-dimensional image. This is what you will be seeing at the lab experiment part of this lecture. All right. So I'm coming to an end with the theoretical part of my presentation. I'm just showing you some gradient coil systems, how they are built up, how they are turned all around. So you can see how small or big the imaging volume can be and how interesting turns and shapes we have with these gradient coils. This is a whole other story, how to design a good gradient coil. And also the receiver coils which in this case is a simple loop receiver coil without any further modifications. And last but not least, let me emphasize the safety protocols of an MRI experiment. It's very important that nobody, including you if you are working with an MRI scanner, you're not allowed to enter without precautions to the scanner. So even if the scanner is not doing any measurements, the external magnetic field is present. It's always present. All right? So if you enter with a coin in your pocket or with a pen in your pocket, they can become bullets. And they are very, very dangerous for patients or others working in the same magnet room. So you always need to empty your pockets, remove your watch, remove your telephone, magnet card, coins, and everything. You can see the image here, how a simple chair can be sucked in by the magnet. It's very, very dangerous. So never forget, even the scanner is not performing any measurements, the external magnetic field is always turned on. Yes, so patients with pacemaker are strictly forbidden to enter. We need to safety check them, obviously. Other patient comfort features can be the acoustic noise during measurement, but headsets are very useful, and we need to pay attention to the absorbed energy by the patient due to the radio frequency excitation. We know that the main goal is not to heat the patient, but as a side effect, sometimes it can happen, but it's always monitored, and there are safety protocols which prevent overheating. And also, as we are turning on and off these gradient currents, we can induce nerve activation very easily. So thank you for your attention. If you have any questions, I will be eager to answer after the lab video. And thank you very much.
Well, thank you very much, Istvan. So you don't want to answer any questions now, or?
Feel free. Okay, that's.
Yeah, I don't know. So I saw that Tobias, has your question been answered in the presentation, or you want to still interact with Istvan?
Can you hear me?
Yes.
Yes.
Yeah.
My question was related to the magnetic field switching. Like, I actually never saw MRI in operation, like for real. I only remember them from movies, and then there was this clicking or switching noise. Does this noise come from the magnetic field switching, and at what frequency does the magnetic field switch? Like, there was some information about frequency, but the protons, but like this frequency seems to me it is rather high, because a magnetic field at this strength switching this fast would, I imagine, would require a lot of it would be very difficult to achieve. I don't think it's impossible, but yeah. So my question is, what frequency does the magnetic field switch?
All right. So the external magnetic field is constant, so it does not change at all. It needs to be constant and homogeneous. The B0 magnetic field. Also, NMR, when we do spectroscopy, so when we do not want spatial encoding, there is no noise. It's completely silent. We just apply the radio frequency magnetic field, we wait, and we do the measurement. However, when it comes to MRI, so when we want spatial encoding, we apply the gradient coils. And this is what creates the noise. When you apply a magnetic field, when there is an external magnetic field, and there is a current, and you turn on and off current in a loop, in a wire, it's going to create noise, because this is basically a stereo headset without a membrane. So what you keep listening to, or what you hear during an MRI data acquisition, is that with the gradient coils, you encode the spatial location, and you turn on to encode one line or one location, you turn it off. So if you just turned on the current and you left it there wouldn't be noise. But because of the constant on and off, switching on and off, this creates this tuck, 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 not noise. So
yes,
this is it. The frequency of the noise depends on the measurement protocol of the sequence. You've seen how many different contrasts can be achieved. Well, based on this contrast, there are different sequences. Yes, so the noise differs in that way. But what I can tell you with the frequency, so the ramp up and the ramp down time, so the time that is required for the gradient coils to go from 0 to maximum value, it's around 10 to 100 microseconds. So this is very low, and this creates this noise around the kilohertz range, if I'm not mistaken. And one last thing regarding the noise, the higher resolution you want to achieve, the greater the noise will be. Also, so if you're not going for a high resolution, you can make kind of a silent sequence, but the clinical value will be not that high. Sometimes patient comfort comes first.
Okay. Thank you.
Have I answered? Okay.
Yes.
Okay, thank you, super. Are there any other questions? Okay, so István, thank you for a very clear presentation. You now switch to the lab work immediately.
Yes,
okay.
It's downloaded on my PC as well, so I hope that the sound will be better than for my own presentation. We'll see. Okay.
Okay. How much time do you think you will need for the lab?
For the lab, it's 12 minutes. 12
okay,
minutes.
Perfect. Let's see.
That's a pre-recorded stuff, and just a moment. Okay, can you see a guy in a lab?
Yes.
All right, so this is not me, this is one of my colleagues. So they were very eager to prepare this lab mashup for you. So there you go, enjoy.
Well, we cannot hear it. You might
Pardon?
have to. We cannot hear it. It's without tone.
István, maybe try to reshare your screen and share the sound as well.
Yeah, just a moment.
Welcome everyone. In this short video I'm going to present you some technical aspects of how magnetic resonance imaging, or MRI in short, is performed. Let us start with nuclear magnetic resonance, or NMR. We put water molecules in a high enough magnetic field, which is 7 Tesla in our case. Such a high magnetic field is produced by a superconducting coil. This magnet has been set up in 2012. Since then, more than 100 amperes current has been flowing through it. To maintain this high magnetic field, we only need to keep it in a cooled environment. Such a cooled environment is realized using liquid helium. Until we store the superconducting coil in liquid helium, the magnetic field will remain. In 100,000 years, only half of the magnetic field will diminish. The small nuclear magnetic moment of protons is aligned with the high magnetic field produced by the superconducting coil. However, if we somehow tilt the magnetization of the protons, then the magnetic moment of protons start to spin around the magnetic field produced by the superconducting coil with a frequency of 300 megahertz. This is the so-called Larmor frequency. Just like the children's toy, just a little bit faster. Such a spinning magnetic moment also induces a voltage in a solenoid coil. Interestingly, this solenoid coil is also the instrument we tilt the magnetization with. The solenoid coil is attached to two capacitors that we can use to match the frequency of the material we place inside the NMR. When you look at the circuit, you can see beside the solenoid coil two trimming capacitors. These are adjustable capacitors that provide a matching in the frequency. By adjusting with these knobs the capacity of the two capacitors, we can match the alarm frequency. If you look at the screen, you can see that by turning these knobs, I can tune the frequency and power of the dip. This is important because we also need to match the frequency of the NMR nuclei and achieve a superior dip. No less.
Now let's take a look at a real NMR measurement. First of all, we apply a so-called 90-degree pulse. This pulse rotates the spins from the z-axis into the xy plane. After this, the spin directions rapidly lose their coherence, which is the so-called dephasing effect. The dephasing is due to the fact that each NMR magnet has an imperfect magnetic field that is not uniform. Therefore, each nucleus spins with a little bit different frequency. The absorbed NMR signal is known as a free induced decay or FID. We can see the result of this measurement for the pulse and the resulting FID on the right side of the screen and the pulse sequence on the left. On the right side, you can see both the pulse and the decay that follows. On the left side, you can see the 90-degree pulse and the receiving sequence. Once we acquired the FID, we can go one step further and apply a second pulse after the FID has decayed. This is a 180-degree pulse, which rotates the spin's direction, and this generates the so-called spin echo. Várjuk, amíg újra elindul, aztán vágás. Here we can see an animation about the principles of the spin echo. After a 90-degree pulse, there is a 180-degree pulse followed by the echo. The spin echo is essentially the effect of reversing time for spins which then recover the phase coherence. On the left side, we can see in column 5 the 90-degree pulse, and in column 7 the 180-degree pulse. And on the right side, we can see spin FID followed by a spin echo. Now let's see a measurement in live. While we are waiting, let me explain the spin echo with a popular example. Imagine that a turtle and a rabbit are competing and running, but the rule of the game is such that after a given time has elapsed, both of them need to run backwards on their original track. Quite clearly, they will both cross the finish line at the same time, unless, of course, one of them is cheating. This is essentially the concept of spin echo. The echo can be Fourier transformed, which gives us the NMR signal. We will look at this in a moment. First of all, we can see the FID before the 180-degree pulse, which is followed by the spin echo. Let's look at the Fourier transform.
Now, let us turn to the case of MRI. How can we exploit the concept of spin echo for MRI? We know that the spinning frequency of nuclei depend on the magnetic field. Well, we can apply a magnetic field distribution or a magnetic field gradient This essentially encodes the position of the nuclei into the spinning frequency, which means that every nuclei acts as an oscillator with a different frequency. For magnetic resonance imaging, we thus need two kinds of coils. First of all, we need a coil that provides the magnetic field gradient. Second of all, we need a so-called birdcage coil. This coil consists of copper lines connected by capacitors. This birdcage coil is widely used in commercial MRI devices. For example, on the screen you can see a device for head scans in MRI measurements. In this experiment, we use a small object consisting of 3 × 3 holes filled with simple tap water. Such a sample that imitates an object under study is called a phantom.
We can now perform the experiment with a suitable pulse sequence. Such a pulse sequence consists of a radio frequency pulse shown in column 3 and some gradient pulses shown after column 5. The so-called gradient echo can also be generated while applying a magnetic field gradient along the x-axis.
The gradient magnetic field in the x direction is produced by this. This is called a gradient line.
The echo looks quite similar to the previous case, but its Fourier transform consists of the one-dimensional image of the sample. Now let's measure the gradient echo. Now, the measurement is done. Let's take a look at the Fourier transform of it. As you can see, the 3 distinct signals in the Fourier transform show the 3 distinct holes along the 3 × 3 water-filled phantom.
Once we have an x-directional magnetic field gradient, we only need to apply a gradient in the y direction as well. This way, a 2-dimensional image can be obtained. To do this, we only have to use the same gradient line as before. If we apply the pulse sequence, we can obtain a picture in 2 dimensions. If you come a little bit closer, you can see the characteristic sound that the coils make while this measurement is underway. Just after a minute, the 2-dimensional image of the phantom forms quite clearly. As you can see, all 9 water-filled holes are shown in this image. Although we only explained the basic principles of MRI measurement, you can see how this can be a widely used and well-regarded measurement in medical imaging, preclinical studies, and non-invasive animal studies. We thank you very much for your attention and have fun while doing MRI.
Thank you very much. Yeah, you can see that your colleagues had fun in producing this video. Are there any questions? Okay. Well, I think it has been very, very clear, your presentation, also the video from your colleagues. Okay, then thank you very much.
Thank you very much.
For everything. That's very, very nice.
Thank you very much.
And then I hand over to Sila. Sila.
Yes, I'm here. Can you hear me?
Yes, we can hear you.
Okay, good. And then I'm going to share my presentation. Is it okay? Kirsten, can you show?
I can see it, yeah.
Yes, okay. Then, of course, excuse me, just thinking about other things. Nice to meet you. I'm Cira Pesniak. We have a lot of email exchanging during this half an hour. And I'm a medical physicist, and I work in a radiation therapy center, mostly on external beam radiation therapy. And today I'm going to show you some basic information about the external beam radiation therapy. I hope that you can, I will close the chat. I would like to see your answers, and also I would like to make some interaction with you, and please answer me on the chat, or you can also switch on your microphone. First of all, some history, but only just one slide, because everybody speaks about history. And of course, the history of radiation therapy is also start with the X-rays by Wilhelm Röntgen, and of natural radioactivity by Henry Becquerel, and after that, Marion Pierre Kulisberg. When we speak about external radiation therapy, then the source is out of the patients. You can hear the source, here the tumor of the patient, and here this is the whole patient. And the patient lies in a couch, and an external source of ionizing radiation is pointed at the particular part of the body. We have different equipment for the different purpose. First is the orthovoltage X-ray are used for treating mostly skin cancer and superficial structures. Here you can see it. This is a tube of X-ray, and it can change it, and also the kilovolt energies also can be changed. It depends on the type of tumor. Then we use the megavoltage X-ray to treat deep-seated tumors. There can be any kind of tumors: bladder, bowel, prostate, lung, brain, or everything. And also for the same accelerator, we can receive the megavoltage electron beams. They are typically used to treat superficial lesion extended to deep of approximately 5 centimeters. It is increasing beam energy corresponds to greater penetration. But the electron beams are not valid for the deep-seated tumors. Some basic definition. When we receive the new accelerator, then mostly we receive some treatment planning system. The treatment planning system need a lot of beam data. How to say, we have to configure the treatment planning system. And this is the reason that we need to make a lot of measurements. First, one of the most important is percentage depth dose. There is a differences between the photon beams and for the electron beams. You can see here the photon beams. Here is the source, patient, and there is some special point. If you look at this graph, here is the dose in a percentage. We always make measure the maximum dose. It is the first, what is the most important. The maximum dose depends on energy. And here is the surface dose. You can see that the surface dose is not the same as a maximum dose. When we go back for the orthovoltage, kilovoltage energy, in this case, the maximum dose and the surface dose are the same. Now we have a surface dose at approximately 30–40% of the maximum dose. Here the maximum dose is 100%, and after that, then we have dose smaller and smaller when we go depth of the tissue. We have this special part, it's called build-up region. For electron beams, we also have, and therefore we have also for the photon beams. They're in the depth region between the phantom surface and the depth of those maximum. It's called build-up region. And you can see here for the PDD for the different energies. Here is for the kilovoltage energy, and also when we have different surface distance. This is the source surface distance. For the orthovoltage matching can be different. And after that, you can see here for the cobalt unit. This is for the cobalt unit, cobalt 60, for cesium 137, and after that for the different accelerators. If we have a larger energy, then the dose maximum will go into the deeply into the body. And mostly we use 6 MV. We always speak about energy and always use the MV. It is because we use this voltage what is needed for the accelerating of, and this is the reason we use megavoltage energy only for the cobalt, and after that for the accelerator MV. Then the percentage depth dose for the PDD, this, for electron beam, you can see for the photon beam, and now the electron beam. The electron beam surface dose is larger, more than 80%. After that, we also have a maximum dose, and there are some special definition. Here is a maximum range. Dmax is defined as the depth at which the extrapolation of the tail of the central axis depth dose curve meets the Bremstein background, the maximum range. Then the second one is practical range, RP. Here is. This is definitely the depth at which the tangent plotted through this steepness section of the electron depth dose curves intersect with the extrapolation line of the Bremstein tail. This is the Bremstein tail. RP. Then depth RQ. And RQ depth is defined as the depth where the tangent through the dose inflection point intersects the maximum dose level. And after that, we can calculate the electron dose gradient, G. It is defined as low. Here, the definition. And you can see also for the electron beam, there is a different shape of PDD, depends on the energy. After that, it's also very important, and we also have to measure the dose profile for the photon beam and also for the electron beam, but there is no larger differences. I'm going to show you only for the photon beam. This is the central region, this part. It is a profile flat in 80% of central portion of the field. This is at 80%. And everything under this section. This is a central region. We can find the penumbra. It's typically defined as the distance between the 80 and 20%. This is the penumbra side. And the umbra, it's typically less than 1% dose of the central axis. It is a central axis dose. Central axis dose. And this part is penumbra. It is always under the 20% of dose. And we can also find the geometrical field size, or somebody used the normal field size, indicated by the optical light field of the treatment machine, and usually defined as the separation between the 50% level points on the beam profile. That here is this distance is a geometric field size. Then we have a dose distribution curve. We use the Isodose curve, and are lines connecting points of equal, it is very important, equal dose in the irradiated medium. They are usually drawn at regular intervals observed dose and are expressed as a percentage of the dose at reference point, which is usually taken as the Zmax point on the beam central axis. Here you can see the Isodose curves for the electron. If we have larger energy, here is a 16 mega electron volt energy. It's deeper the Dmax, and the deeper the Isodose curves. And here you can see for the 9 mega electron volt electron. And it's very interesting that these curves go out of the field. They have a bigger scatter as in photon cases. Here you can see the photon beams. You cannot see this scatter of the beam, and but you can see the differences between the different energies. If you have a larger energy, the dose maximum is larger. Deeper. It is very interesting, for example, when we would like to match the photon-electron field. In this case, I have to be very careful because we can receive some special Dmax between the near the border of the two fields. Then I'm going to show you some toolbar for the radiation therapy in between the 60s and 80s. And there you can see that no CT scanner. They can use only the X-ray machine, but it's a planar 2D X-ray machine, and they can find somehow the body shape. They use this kind of drawings, and also they use the SSD techniques. That means that use the constant search surface distance. For the linear accelerator, this search surface distance is 100 meters. For the cobalt unit is 80 centimeter. And we can also irradiate only with the square field, rectangular shape of tumor, but we know that not rectangular. It's changeable. You can see here also the construction of cobalt unit. That time mostly used the cobalt units, but for example, Varian company had accelerators. It's named CLINAC with 4 MV and 6 MV. But here you can see the construction of cobalt unit. Here is the cobalt unit if in a storage position, here when it's irradiated, and it's big shielding of the head, and this part, the collimator part, and it is a storage position, and we would like to irradiate the patient. The source has to be put in this position. There is another, this is a source on rotating cylinder, and there is in a storage position, and we would like to irradiate the patient. Can turn down, and in this case, using the collimator system, we can irradiate. It was the first rotate cell in Hungary made by the Hungarian company for the cobalt unit. You can see here the table, the patient, and the cobalt unit can turn around the patient, and we can change also the field size. Then here's the treatment machine construction for linear accelerators. We mostly use this linear accelerators. You can see the pictures here, and there is a basic elements of it. First, one of the most important, of course, electron gun with accelerating a waveguide. Here always can be the vacuum in accelerator. This reason we need a vacuum pump. Then here is a microwave power sources, some pulse moderator, gas system pressures for the moving. We have a water cooling system, inner and outer. And if we receive the beam, here is a pulse electron beam. We have an outdraw pole magnet to change the beam direction. And here you can see the target where we receive the Bernstein X-ray. And here is the exit window and the collimator system. When we have primary collimators and secondary collimators, and here is a flattening filter. Flattening filter, with the flattening filter, we can change the shape of the profiles. I'm going to show you in the next picture how it looks when we move out the flattening filter. We have here two dual ionization chambers. They made the measurements in the same time, and if the difference is larger than 2% of the two measurements, then the accelerator stops. Also, we have here upper and lower jaw. With this jaw, we can change the field size, and here is the multi-leaf collimator option. And of course, this is the beam center axis and the coach rotating axis. It have to be calibrated to be in the same way. This part we called a linear accelerator head. And here the special treatment port for the patient. You can see here the setup of construction of the linear accelerator's head, and now you can see in a better view the head of the linear accelerators. It's the same how it's mentioned previously. Ionization chamber, secondary collimator, multi-leaf collimator. You have always the flattened X-ray beam, and this part is the central axis and the patient. There is a lot of different scatter situation. And if I take out the flattening filter, before this profile was flat, and now we received this shape of the profiles without flattening filters. Okay, for the dosimetry, we use a lot of different equipment for a lot of different phantoms and ionization chambers. And now you can see here the basic element. Without this phantom, we cannot work in radiation therapy centers. Is a water phantom. After that, we use a different ionization chambers. Our ionization chambers is quite small. It is the biggest. It is a farmer type chambers. And when you want to measure in air, you can use this build-up cup to compensate this build-up region, what I showed before. The farmer chamber we mostly use for the absolute calibration of the beam. There is also a special chamber called plane parallel chamber. Plane parallel chambers is two types: Roche chamber and Marcus chamber. It's mostly used for the electron beams. This is a very, very special, I think nowadays, one of the best detectors. It's a diamond detectors. It's very, very small. The active value of the ionization chamber is very small. You can see in the rower. And we always you have to use some kind of those electrometer. And we have also different 2D measurement, 2D devices. For example, it can be the semiconductor or ionization chamber matrix. And also with this, we can measure somehow on 3 dimensions. And we also use the different anthropomorph phantoms, which has the same construction as the body tissues. And we use a lot of different softwares. This software, for example, for the map check semiconductor matrix, and we can make a measurement from the, we can compare the predicted dose and the measured dose, and we can evaluate our work. Here you can see the small video. I hope that it will work. How can set up the water phantom? Oh no. Yes. Can you see here?
Yes. You can see.
Thanks.
Yes, you see.
You can use the wireless auto setup. These new water phantoms are very, very nice and work quick. You can full with water, of course, and there is a special folder of ionization chambers. There is a fully automatic 3-point leveling, and the chamber can move in all directions, all 3 directions. Here is the chamber. You can see it's a semi-flexible chamber, also very small dimension, mostly used for photon beams. And you can use this kind of chambers to the photon beams to centimeters. And it is a reference chambers, and you can see here the software, how it's measured the profiles in one direction, and also always we need to measure it in the other direction, and after that we can set up in the center line position. And when you've finished your work, it's very easy to remove the phantom. Then we also use the film dosimetry. It is a monomer, and after the irradiation, it can be polymerized, and you can see we can irradiate with the different field sizes and the different doses. And we have a special software, and we can see in the 2-dimension and 3-dimension the shape of the beam. Also, we use it for the verification of the treatment planning, of the treatment plans received from the treatment planning system. It is the irradiated film, and this is from the treatment planning system fluence of the beam. And you can see here the when we compared. Here is the differences. Also, we can use the special softwares. There is the future, the 3D dosimetry, it's a geodosimetry. Also, there is a lot of different kind of geos. And if you make a treatment plan in the treatment planning system in 3-dimension, then irradiate the gel, you can receive the quite some results. There also can be used different detector systems, how we can evaluate which the dose was irradiated. We need also the patient fixation in the head and neck region. We can use the special thermoplastic mask to make a fixation of the body. It's very interesting because in most cases we have to irradiate the patient approximately with the 40 to 90 gray. It is a very big, large dose, and the patients receive it in a fraction dose. It means that every day receive 2 gray, and in this case we have to repeat it 20, 45, 50 days. And if they are not fixed, good positioning, and they are not fixed, then we cannot irradiate the tumor with something else. Here is the first CT-based treatment planning from 1978. You can see that there is noise and a lot of artifacts. And in that the days we cannot have, for example, DICOM structure, and mostly they can use the digitalization system. Also for the medical imaging is very, very important. Do you know which kind of equipment is it? No, nothing. It is a CT. Also, the other one is a PET. You received some information about this before. And now it is the last one, the MRI scanner. I think it's also very important to use all these imaging modalities. We make our treatment plan on the CT because the CT gives information about the density of the tissue. Here you can see one CT simulator. It's equipped by a special laser system, And we also use the flat table because we can use the spoon shaped table. The anatomical structure will be in another place, and because the accelerator table is flat, we also have to use the flat table for the CT. We also use the special phantom for the calibration of the CT. For the treatment planning system, we have Hansfield number and relative electron density, and for the every CT, we need to make a special calibration curve and upload it in the treatment planning systems. You can see in this picture, when we use the density correction, we receive this kind of dose distribution, and if we do not use the density calibration, only when we think that everything is waterproof. Thank you. And here you can see one CT examination in the CT simulator. It is anthropomorphic phantom. You can see here the lasers there was in the wall, and this phantom contained different parts of the lungs with the roses and the soft tissue density. Here is a special ball for the setup of the patient, and find the reference image, and here topogram of the CT, and you can say the transverse lines of the CT when the CT started to scan it. Here is the lung part and the soft tissue part. Then when we have imaging for the MRI, we receive the very good shape of the soft tissue. You can see the details. There is the PET, we mostly use the FDG PET, I mentioned yesterday, David. And also here is the picture for the CT. You can see the differences here. If somebody has a brain tumor, you always have to use the MRI modalities also, because in other case we cannot see anything. And when we make a fusion, you can see here that, for example, for this patient, we have here the tumor. The brain do not have a tumor because the FDG is the glucose, and the brain has a high uptake for the glucose. Here is some special images. I would like to ask you, do you know which modalities are here? Is here? Who know which modalities is? CT, MRI, PET?
MRI?
No. Other idea?
CT.
CT, yes. And what do you think? Where are you in a head, in for example, breast or pelvis? Somebody put in a chat that head. Yes, it is somewhere here. If you can see my picture, lower head. Yes, the teeth. Then this image is PET, MRI, or CT?
PET.
It is a PET. Now you can see it's the same patient, and here is how is something there, but we cannot say where is exactly and what volume is there. But if you make a PET CT, then you will receive the full information. Also, what is this? PET CT or MRI? I received one MRI. Yes, this is MRI. For the MRI, it's a no cost density. It is, you can see here the cost density, and here is it is a T. And if we use the MRI PET fusion, that you can see that here is the tumor also, but in this picture we cannot see exactly. Then the next one, where is this? And what is this? What do you think? PET, CT, MRI? Yes, PET. This is a PET. And do you know where is it? Yes, it's PET. No answers. Maybe here.
thoracal area.
And what is this?
Maybe
Part of the body?
liver.
Yes, it is a liver. Good. Yes, it is a liver. And when we make the fusion, we can see that there is a liver tumor of the patient, and it's very shaped. Also, we need to use it for the prostate cancer. If you use only the CT, you cannot see the differences between the bladder, prostate, and rectum. But when you use the MRI, then here you can find a very good contrast of shape. This is the bladder, this is the prostate, and this is the rectum. And in this way, we can make a better irradiation of the patient. It is also one of the very interesting part because there is something in the first view, we think that it's whole the tumor, but when the patient sent to the PET CT, then you can see that the center of the tumor is here, and now here you can find some scattered tumor cells. It is some more examples. It is a lymph nodes. There it is very, very interesting small tumor in this part of the body. And this is, it is not the tumor, it is a bladder. The bladder has the uptake of the FDG. The tumor is here. It's a soft tissue sarcoma. Then, and there is some definition of volume. We define the gross tumor volume, but not we. It is the work of the doctors, of the physicians, who have to delineate the gross tumor volume, clinical target volume, and internal target volume, and the planning target volume. The physicists always make a plan for the planning target volume. And there is some volume definition of the organ of risk. We have to spare it. If we will irradiate the organ at risk, then we will make a side effect. There is an early and late side effects. For example, if you see one patient, here is the spinal cord, esophagus, there is a lung, is all of them organ of risk. And here is the heart, aorta, it's a liver, and we will have here the kidney, and they are the organ at risk. Also very, very important, the delineation of the volume. It was the different studies where the same, the radiologist, oncologist work on the same CT set, and you can see that they delineate different kind of shape of the tumors, and it's a very big problem. They need a continual education all of the doctors also. The conformal radiation therapy used the 3D reconstruction of the target. We have here the MLC, multi-leaf collimator, and in this way we can change the shape of the beams. And we use the SRD techniques, source axis distance. We need to set up only one point, and all movement of the accelerators and table will be around this one point. Here is some conformal plans. It always depends how is the high expertise of the physicist. If somebody is a higher expert on the radiation therapy, can make a better plan as who is a beginner. Always the problem to check all the plans more times and for the more patients. There is an intensity modulation radiation. When we speak about the conformal therapy, then we have a homogeneous field. When we speak about intensity modulated radiation, we can change the intensity of the voxel from the voxel to the voxel for the small volumes. Here you can see the special kind of irradiation with the dynamic multi-leaf collimators. And here, if we have here, for example, some organ of risk, we can spare it. And this is one treatment for the IMRT. It is a linear accelerator. You can see the head of the linear accelerator, collimator setups, accelerator tube, a bending magnet. Here is the electron beam. For the bending magnet, here is the target, and after the target we receive the Bernstein X-ray, and all our accelerators are equipped with the portal imaging device. It is an amorph silicium device, and it is useful for the measurement of the dose, because we have a predicted dose for the treatment planning system and measure those, and if it match as a minimum 95%, after that we can irradiate the patient. Here is the patient. This is the multi-leaf collimator system. It's a small metal part, and every metal part is an oven motor. It's and on a computer, we need a computer for the moving this parts of the accelerators and a special software. And here you can see the prostate tumors. Here the prostate. Here the organ it gives is a rectum. It's a special, very special organ for the radiobiological side. We need to spare this part of the rectum very well, because in other case they lose the functionalities. And in this plan, 5 IMRT beam was delivered. In this case, we have approximately 15 minutes for the treatment, and plus set up the patient, of course. Now, I hope it can work. Mostly use this intensity modulated arc therapy. It's IMAD. During the irradiation, the gantry can turn around the patient, and in this way we can spare better. It is a parotis, it is an oral cavity. There are the spinal cord, and we can spare it better way in this way. And the whole treatment is 2.5 minutes. It is very, very short treatment time, and very precise. Also, we have to use some image-guided radiotherapy equipment. Like every accelerator is equipped with the COMBIM CT and the electronic portal imaging device, or in a brain lab system, we have exact tract with the infra source and kilovoltage Röntgen imaging devices. And later, Gabor Stelzer are going to speak about CyberKnife. Here the images for the IGRT. When we use the EPID, here is the DRR, digital reconstruction radiograph from the treatment planning system, and it is the EPID picture. And when we put matching the two pictures, we can see the how we can change the position of the patient, that the irradiation will be on the right position. We can set up the patient on the 1 millimeter precision. Also here you can see the COMBIM CT. There is the top CT. We call it top CT when this CT image is set when we use for the treatment. And here you can see the COMBIM CT images. It's the quality of the COMBIM CT is a little bit worse, but for the patient setup it's enough. Now we have one problem, that everything is moving in our body, and today we speak about the unmovable CT slices. Now when we irradiate the patient, for example, for the lung tumors, because our lung is move in a larger volume, and here if we have the small tumor, you can irradiate with the big beam, big fields, to that the tumor always will be in the beam. Now here you can see the brief curve. It is a mostly sinusoid curve, and if we can manage that, we always irradiate the tumor in the same position, then we can use only this small field, and we can spare the health tissue in a larger effectiveness. And this is my presentation. If you have a question, please ask me. And after that, after the break, Gabor Stelzer will show you the very special machine CyberKnife.
Okay, thank you very much, Sila. So yes, are there any questions? I think you were already quite interactive with your with the presentation, maybe. Yeah, no, don't see any further questions. So it's now, well, 10:39, 10:40. I suggest we break until 10:55, and then we ask Gabor to start then at 10:55.
Okay.
So as Sila said, we have the presentation and the lab on CyberKnife after the break then. Yeah. Okay. Good. Let's go for a break and see you then at 10:55 for the last session of this medical physics. See you. Hello, Gabo. Are you already here?
Hello, welcome. Yes, I am here now.
Hello, Gabo. Just to see whether you wanted to quickly check your presentation.
Yeah.
Yeah. You want to just upload the presentation, check it, and I guess you have one presentation and one film, or what do you have?
Both of them will be played as a film. I recorded
Okay.
the voice for the presentation also.
Okay. Do you just want to upload it and try whether the sound plays okay and everything?
Is it okay if I share from my computer?
Yes, please. Yeah. Just go ahead.
Okay.
Just try and share now. We still have 2 more minutes, so then we're on time.
Okay, so do you see my video
we
now?
can see it. Yeah.
Okay. I stopped sharing for a second because I don't know if I share the audio also or now. I will do it again. Share sound, yeah. Okay. Okay. Now I shared with the audio also. Okay, I start, then you can check if it's working or not.
Yeah.
Okay.
Welcome everyone.
Yep, perfect.
My name is Gabor
Can hear the sound.
Okay.
Great.
Okay. Should I stop sharing now?
Yes. Just 1 second. I'm going to admit some more people to the wait. Okay, fine. Okay. Then I guess we're ready to go. Gabor, you're the last the last meters of this marathon of the medical physics presentations. So yeah, the floor is yours. Just go ahead.
Thank you very much. So I will share my screen and start the presentation.
Welcome everyone. My name is Gabor Stelzau. First, I want to thank to the organizers giving me the possibility to talk about our CyberKnife installed at the National Institute of Oncology at Budapest. CyberKnife is a robotic linear accelerator dedicated to stereotactic radiotherapy. First of all, let's see what does stereotactic radiotherapy mean. Under the word stereotactic, we mean something like precise positioning in three-dimensional space. Under stereotactic radiotherapy, we mean high daily doses delivered in a few fractions. The high daily doses start from 6 gray up to 20 gray, and few fractions mean from 1 up to 5 sessions. Always, during stereotactic radiotherapy, small volume has to be treated. The maximum diameter for that is 7 cm. High precision has to apply to keep the safety margins around the target as small as possible. The radiobiological background of stereotactic radiotherapy is that the same physical dose can mean different biological effects depending on the fractionation chain. For example, for conventional radiotherapy of lung cancer, we deliver 30 times 2 gray, which means 60 gray physical dose, what have 72 gray biological effective dose. In a stereotactic way, when we treat a lung cancer, we deliver 3 times 20 gray, which is also the same 60 gray physical dose, but it has biologically effective dose of 180 gray, which is more than 2 times more biological effect than the conventional fractionation. Here on these images you can see 2 lung cancer treatments. On the left side you can see a conventional treatment, daily 2 gray treatment for a big volume which contains the tumor and the lymph nodes in the mediastinum. While on the right side image you can see a stereotactic treatment of an early stage lung cancer, but the volume is very small, so we can apply very high daily doses for the treatment. The stereotactic radiotherapy, or the stereotactic radiosurgery as it was called in the beginning, was started by a neurosurgeon called Lexel in the 1960s. He built a so-called gamma knife device which had 200 cobalt sources around the sphere, half sphere, and the system had a collimator system which looked like a big helmet around the head of the patient. For tumor positioning, they used the stereotactic frame that can be seen on the left upper image, which was a localization frame. With the degree and the millimeter scale of this frame, Lexel was able to localize the brain tumors inside the head.
Gabor, you want to try and do the presentation live?
With this three-dimensional localization system, they positioned the tumor in the focus point of the gamma knife, where all the 200 cobalt sources was aiming in the same focus point. With this method, there was a very high dose in the focus point, in the tumor, and a very steep dose gradient around the target. In the late 80s, early 90s, they started to deliver these kind of stereotactic radiosurgery treatments on standard conventional C-arm based Linux, as you can see on the right side image. They equipped the standard Linux with a special conical secondary collimator system with which they was able to deliver very small beams with very sharp penumbra, and they fixed the head of the patient with the same stereotactic frames to a stand, and this way the patient wasn't able to move the head, so the positioning was very precise. And with the secondary collimator system with more arcs, we could deliver very high doses and very steep dose gradients to small volumes. In the late 90s, they started to deliver without the frame, the so-called frameless stereotactic radiotherapy treatments, because of the development of image guidance. Nowadays we are able to detect the position of the patient and the position of the target very precisely with these kind of image guidance methods. For example, on the right side you can see the CyberKnife system, 2 X-rays sources and 2 X-ray detectors, and orthogonal planar imaging with 2D imaging method, and on the left side you can see a modern true beam, linear accelerator, conventional linear accelerator, and with this With rotating the gantry, we can create a so-called cone beam CT. With this method, we can deliver stereotactic radiotherapy treatments. In our institution in Budapest, the National Institute of Oncology, we have a CyberKnife system. You can see on the image this machine. This is a CyberKnife M6 machine equipped with a multi-leaf collimator system. And this machine is dedicated for stereotactic radiotherapy only. It has the orthogonal X-ray planar imaging system. You can see the X-ray sources on the ceiling, and you can see the detectors in the floor. The 5-dimensional carbon fiber couch can be also seen on the image. With this carbon fiber couch, we can position the patient very precisely. The CyberKnife system is based on a robot. It's called the KUKA robot. It's a very famous robot in industry because they are using, for example, in car manufacturing, these kind of industrial robots. They are very robust and very precise. And in radiotherapy, we place a linear accelerator at the top of this robot. The robot has 6 axes where it can make rotations, so we can orient our radiotherapy beams in 170 nodes, points around the patient, and from every point the machine can aim into any direction onto the patient, so we have nearly infinite number of beams that we can choose from during treatments. The machine can put down its collimator and pick up a different collimator because it has 3 types of collimator system, the so-called multi-leaf collimator, the fixed and the iris collimator. The first collimator type was the fixed cone collimator, where you have 12 different types of beams. The field sizes are ranging from 5 mm up to 6 cm, as you can see on the images. But you have to manually change these collimators. The disadvantage of this collimator that it needs much more time for treatment because it can only deliver circle-shaped beams, so we cannot use irregular shaped fields. So you have to use much more beams and much more directions, and we have to go inside the treatment room during the treatment to change the collimators. With the iris collimator, they made some upgrade of this collimator type because the iris collimator can create the same field sizes from 5 mm up to 6 cm, but it can change the field size automatically, so you don't have to enter the room for changing field size. But still, the field shapes are only circle shapes, so still you cannot do intensity modulated radiotherapy. With the multi-leaf collimator, as you can see on the image, you can create any type of field shapes with 26 leaf pairs, and each leaf pair has a 3.85 mm width at the 80 cm source axis distance, so it's very small leaves, and you have a maximum field size of 12 times 10 cm, and the MLC can do full interdigitation and 100% over travel. The radiation transmission through the leaves are below half percent, and with this the machine can deliver the so-called step and shoot intensity modulated radiotherapy. If we remove the cover of the linear accelerator, we can see this. You can see in the middle there is the accelerator tube. On the right side you can see the magnetron and high voltage, the boost transformers and so on. So they had to fit all these things into a very small volume, and they had to keep the weight of this head below 350 kilograms because the robot cannot handle more weight. So all this LINAC head is mounted on the robot, and it can deliver 6 megavoltage flattening filter free beams. The dose rate at 80 cm source axis distance is 1000 monitor units per minute, because you have to be as fast as possible, because the robot has to go through a lot of beams, a lot of direction, so treatments can last long on a CyberKnife machine. So you have to use as high monitor units per minute, as high dose rate as possible. How does the verification and correction works on CyberKnife machine? As I said, we have 2 orthogonal X-ray sources and amorphous detectors in the floor and 5D couch. During the treatment, we are not moving the couch below the patient, because if you move the couch, the patient can feel the movement and will make sudden movements because of the couch movement. So instead of couch movement, we are moving the robot. So if we measure some patient movement, positioning error, then we send this information to the robot, and the robotic arm will put the source and the beam into the correct position immediately. For target tracking, we have some types of tracking. The first tracking type is the 60 skull, the second is Excite spine. We also have fiducial and excite lung tracking, which can combine with synchrony for motion management. It's live tracking during the treatment, so let's say in every 45 seconds we are creating a new image pair so we can verify the patient position. The time intervals between images can be adjusted between 20 seconds and 2 minutes, depending on the stability of the patient. And when we see patient movements, setup errors, we immediately send this information to the robot and it's corrected automatically. Here you see an image pair with 6D skull tracking. In the background, the grayscale image is the DRR, the digitally reconstructed radiograph image coming from the planning system. So the grayscale image is the expected perfect position of the patient, where the patient should be. And the blue scale images, the live images, are acquired by the X-ray sources and detectors. So this is the actual position of the patient. And with image fusion, the system automatically calculates the offset, the differences between the expected and the live image. As you can see on the left column, this is the calculated offset. And as you see on the right column, the applied offsets are the same. So this is the correction values that are delivered by the robotic arm. So the beam is coming for the perfect position of the patient. It's nearly the same with the Excite spine tracking, where we track the vertebral bodies of the patient because it has high densities, so we can see on the image easily. The system can automatically detect the spine position of the patient. If we want to deliver something that cannot be seen on an X-ray image, for example normal tissues, cannot be seen on X-ray imaging because it doesn't have higher density than the neighbor tissues. So if you want to see some normal tissue tumors or targets like prostate or liver metastasis or lymph node, then we have to use the so-called fiducials. These very small gold markers are implanted into the target or very close to the target before the whole treatment process. So before the planning CT, 1 week or 2 weeks before the planning CT acquired, we place 4 gold markers into the tumor or very close to the tumor. And the gold markers has very high density, so they can be seen on an X-ray images. So if we make the tracking of the gold markers, we can make the tracking of the tumor, which is around the gold markers or between the gold markers. This way we can make visible nearly all sites or type of tumors where we can implant these kind of gold markers. This is an image of an Excite lung tracking method. With the Excite lung, we can make lung cancer patients treatable if they are not applicable for gold marker insertion, because a lot of lung cancer patients has in bad general conditions, so there is no one who can risk the gold marker implantation. So instead of that, the system is able to detect the shadow of the tumor on the live image, because the lung tumor has higher density than the lung tissue itself. So the algorithm is capable of detecting the shape, the shadow of the lung tumor. And we combine this with synchrony tracking, because the lung tumor is moving with the breathing movement. This is called the respiratory motion tracking. For that we need a special planning CT. For that we do a breath hold CT scan. We acquire 2 image pairs or sets, one in inhale phase and one in exhale phase, to measure the 2 end position of the tumor. We use an optical camera during the CT scanning, and we use special patient immobilization devices, and we always have to do a photo of the patient position to be able to reproduce the same position. During the treatment, if we do respiratory motion tracking, first, if it's a lung cancer patient, we have to set up the patient according to the spine, the vertebral bodies of the patient, because from the shape of a lung tumor we cannot set the rotational errors of the patient, but we can set this up with the help of the spine tracking. When we are sure that the general setup, the general position of the patient is correct, then we move to the second step, when we shift from the spine setup to the lung tracking, the Excite lung tracking mode. So we shift the patient from the spine isocenter to the tumor isocenter. So we will see now the tumor on the X-ray images. And we have to build the synchrony model. We have to acquire 15 image pairs in 15 different phases of the breathing cycle. So one inhale and exhale phase is a full cycle. From that we take 15 different phases and acquire X-ray images. So we will have information of the tumor position in 15 different places, and we make a correlation model. We correlate this tumor information, tumor position information, with the chest wall position information, what we acquire with the help of an optical camera that you can see on this image. With the help of the optical camera we continuously measure the 3-dimensional chest wall motion, and we correlate this chest wall motion with the tumor motion measured by the X-ray imager. Here you can see one example of a synchrony model, 15 different phases acquired in different breathing phases, and on the left column you can see the correlation values of the model. These correlation values are showing us what is the difference between the expected position and the real position of the tumor in each phase. This correlation error should be as low as possible and has to be compared with the applied safety margin in each case. On this video you can see respiratory motion tracking treatment. You can see as the patient is breathing, the robot is moving together with the tumor. It's a very small movement because the tumor moves only a centimeter or 1.5 centimeter, but you can easily detect the robot motion. With the CyberKnife we have some radiation protection issues. For example, during the treatment we are using a lot of nodes, a lot of direction, and the machine has a non-isocentric setup. So radiation can go to any wall of the bunker from any direction, and because they are intensity modulated treatments we are using very high number of monitor units. We also have scatter and leakage that we have to handle during radiation protection. The commissioning of the machine is quite complex. We are using a water phantom and we have to use small field dosimetry because the smallest cone that we are measuring is a 5 mm cone, so we have a very small fields that we have to measure. We have to use an unshielded diode. Usually we use a so-called microdiamond during our measurements, which has to have a very small sensitive volume to be able to measure these small fields. We do profile measurements, tissue phantom ratio measurements, and we measure the output factors, and we had to do some additional measurements. For treatment planning we have a Precession treatment planning system with different calculation models. With the most modern technique is the Monte Carlo calculation, which is a type C calculation algorithm which simulates the reality, so it simulates the real dose. We have to import the measured data for treatment planning system configuration. We have to create a model and modify this commissioning model. For QA program we have a QA book and recommendation and records. We do daily QA, end-to-end test and patient-specific QA, and also machine QA. You will see more information about this QA test in the next session, the laboratory session about the CyberKnife. Shortly, I just show how we do these kind of tests. We do output check every morning with a small ionization chamber with a fixed setup, fixed robot and couch position. We check that the delivered dose is equals to the desired dose. We do automated quality assurance, the so-called AQA test, for very fast and very quick geometrical test. From two directions we check the position of the robot and the imaging system. With the picket fence test every morning we check the stability and the precision of the MLC. With the plan verification we do patient-specific QA in a Lucy Phantom with a very small ionization chamber. Before the treatment of every patient we have to measure every treatment to verify that the patient will receive the expected dose. With the end-to-end test, we have to measure the total targeting error of the machine for each collimator for each tracking. The garden fence test is dedicated for MLC calibration check. Thank you for your attention, and I would be happy to answer your questions if you have any question. Thank you.
Okay, thank you, Gabor. So yeah, although this, maybe you can turn on your camera as well. Okay, so are there any questions? Well, I think maybe, yeah, then you can jump directly into your lab presentation.
Yes.
Yeah.
Yeah, I will share my screen again.
Okay.
Okay, then I start.
Welcome
Yeah.
everyone, I am Gábor Stelzer, and this is our cyberknife at the National Institute of Oncology. As I have shown you in my presentation, this is a robotic arm-based linear accelerator. This robot can put down this collimator, the multi-leaf collimator down here on the collimator exchange table, and pick up the other collimators, the fix and the iris collimator. With this manipulator, we can irradiate the patient laying on this couch, and we are doing the image guidance, the image guided radiotherapy with the imaging, the X-ray sources and the X-ray detectors on the floor. And this is the orthogonal X-ray imaging what we do during the treatment. On the cyberknife we have to do strict quality assurance, and in this practice I want to show you the most used measurements what we do. First of all, I want to show you the daily QA, the ionization chamber measurement, when we measure the output of the accelerator. For output measurements, we use this solid water phantom, so-called slab phantom. In this slab phantom, we can insert the ionization chamber. This is a semi-flex ionization chamber, and we can insert inside the slab phantom. Exactly 1.7 centimeter deep below the surface of the phantom. And then we position this phantom below the linear accelerator. Into the middle of the field we position the ionization chamber. This is the manipulator of the hand pendant of the robot. With this we can drive the robot into expected position. And we position the beam exactly above the ionization chamber. Then we put the final slab to make the exact depth of the ionization chamber. For daily output check, we set a 10 cm by 10 cm field size, and we deliver 200 monitor units. And we collect the measured charge on a so-called electrometer connected to an ionization chamber. Then we correct this charge with the current temperature and current pressure to get the real result for today. And the tolerance for absolute dosimetry is 2%. The pins has to go inside the exact holes, and with the screws we have to fix into the correct position. And with this film holder I attach the film on the MLC collimator. For picket fence test, we deliver 10 fields connected to each other. Each of the fields has a width of 10 mm. For each field, we deliver 170 monitor units on the GAF chromic film connected to the edge top of the multi-leaf collimator. This is how the first beam is delivered, and then the fields are delivered one by one. After the picket fence test, we can check if the 10 different fields fits to each other or not. The third daily QA is the so-called AQA, Automated Quality Assurance. Is made by this phantom. We position 2 pieces of GAF chromic film inside the phantom, and we put in this cube. This cube has a ball inside the middle of the cube, and I position this phantom on the couch. And then we will deliver 2 different beams on this phantom. First, we verify the AQA phantom position on the couch with the help of the 4 gold markers with the fiducials, and if the tracking is precise, we deliver the 2 beams on the phantom, the anterior and the lateral beams. After delivery of the AQA test, we will get this result. And we measure how exactly the ball can be hit in the middle of the circle field from both directions, both from anterior and both from lateral directions. For AQA tests, we load the 2 images, and then with the software we evaluate the targeting precision, and we can see the total radial error is 0.9 mm, which is below tolerance. For end-to-end test, we use this head phantom. In the middle of the head phantom there is a cube which is simulating the target in our quality assurance process. This is the so-called boa cube, and we can place a pair of films inside this boa cube, and you can see there is the target in the middle of the boa cube. With the end-to-end test, we are measuring the total targeting error. We make a CT scan of this phantom, and we make a treatment of this small cube, and we will measure at the end how precisely we can hit the target. These are the laser pre-cut films, GAF chromic films, that is fitting precisely into this boa cube phantom. And then we position this boa cube in the middle of the head. And we position the head phantom on the couch. And we'll deliver a simulated treatment on the phantom. For end-to-end test and also for Lucy phantom and synchrony phantom measurements,
First we check the phantom position on the couch. If any correction is needed, we correct it by the couch. And verify the new position. The grayscale images are the expected position of the couch and the phantom. The blue scale images are the live position of the phantom. And this is the calculated offsets which will be corrected by the robot. If the position is correct, we deliver the treatment on the phantom. During these tests, all the fields are delivered one by one, just like in the case of a real treatment. The results of the end-to-end test can be seen on these gaphromic films. It will be evaluated by the software how precisely we can hit the middle of the ball cube insert. We will evaluate the 70% isodose level on these films. For end-to-end tests, we load the image pair, the film pair, and one background film in one scan. The software makes the image process automatically, and here we see the image pair. One is the anterior superior film and one is the anterior left film. We see the effect of the radiation on the films, and then with the evaluation the system checks the 70% isodose level on the films, and from this it can calculate the total targeting error, which is in this case is 0.5 mm. The tolerance for this is 0.95 mm, so this result is also below tolerance. For garden fence test, we are using the same positioning device as for picket fence, but we will deliver different kind of beams, and this is a monthly QA, not a daily QA, for checking the calibration of the MLC motors. The garden fence test is very similar to picket fence, but here we are applying 15 mm gaps between the fields, so we deliver only 5 beams. For each beam we deliver the same 170 monitor units, so nearly 1.7 gray, and we will evaluate with the software these 5 fields. For garden fence test, we load the films in red channel only, and then we turn off any kind of filter. We load the correct calibration files, and this is how the film looks after processing. And then we run a so-called Bayes MLC test, which is checking the positioning errors of each leaf pairs in 5 different junction positions. And then we analyze the image and we get the results of each leaf banks, the X2 and X1 banks in the 5 different junctions, how precisely the MLCs created these 5 fields. And green means in every position, in every junction, all the MLCs was in the correct positions. As I showed in my presentation, the CyberKnife has a motion tracking option, the synchrony with the synchrony camera, and this phantom is dedicated for the tracking motion, the checking of the tracking delivery. We are using the same ball cube insert and we are placing it into this sphere, and we are positioning on this moving phantom. And we put it under the accelerator and simulating the breathing cycle of the patient. And we are measuring the total targeting error while the target is moving. The Lucy Phantom is used for patient-specific QA. Before treatment, each treatment plan has to be delivered to this phantom to evaluate the exact point dose value in the middle of the target. So this phantom has an even smaller hole for even smaller ionization chamber, so the so-called pinhole, and we are positioning this under the accelerator and deliver to this phantom the real treatment of a patient before the first fraction.
Okay. Okay, thank you very much. So very clearly explained. Are there any questions from the public? So I don't see any questions. Then I thank you very much, Gabor. Very clear presentation. Okay, I see Sila.
Yes, I have some information.
Okay. Well,
We
then I say
received
thank you.
really a lot of project works, and I'm sorry, but I do not want to take a lot of time. Just I would like to show my picture. Here is. Can you see it? Yes.
Yes, we can see the picture.
Okay. We received 16 present top project work for the different topics. And now
Sila,
I would like
sorry,
to
can you
show
maybe
the
put it on presentation mode? Then it's a bit bigger.
Yes, yes. Okay. Now it's okay.
Yes.
And now we collect separately for the medical physics project work, of course, for the nuclear energy. For the nuclear energy, I'm going to show you during the afternoon. And now, please, these teams who are here mentioned to prepare the presentation. They send me the presentation now just to prepare to present it. Each presentation has 7 minutes. Because we received a lot of presentation, and I think we will see more for the shorter time. I hope, because all the presentation is maximum 6-8 slides, just a short to present your work, because we received the longer written text. It is only the presentation. And here is for the team ETF tritium, radioactive sources for diagnostic and therapy purpose. The team Nucleider also use this one, but they make a short video. There is no presentation, just a 3 minutes video. After that, the team Lithuania history of radiotherapy, team TID planning of radiotherapy facility, and team Setka construction and operation principles of linear accelerators. I'm going to send also an email if somebody is not a participant in the morning session, this information, and afternoon I'm going to show for the nuclear energy also the project presentation. Thank you, Kristen. Thank you.
Okay, thank you, Sila. So if I understand right, the jury will take into account the whole text and everything. It's just the presentation should be only 7 minutes.
No. Now is not jury now working. It is only tomorrow for the presentation. It do not mean anything. It is not the result. It is only they can present their work, and that's all. Jury work on it. I will receive the final scores from the jury. Everybody works separately at 10 o'clock in the night.
Okay.
That's all. We will know the final scores tomorrow on our ceremony.
Okay, good.
That's
Thank you very
all.
much. Any questions
results,
from any questions about this? Cannot see any questions. Well, then we can close this the sessions on medical physics, nuclear medical physics now. And as Mattia mentioned before already, I really would like to invite you to join this evening at 5 o'clock the career guidance session. So we have 7 professionals, some very, very inspiring professionals, I find, who will present what they're doing, how they got where they got, and they are able you're able to ask them questions, and I think I think it promises to be a very, very interesting session. So I invite you to join at 5 o'clock this afternoon, unless you want to join this afternoon, where we'll have some sessions still going on generation 4 and on nuclear fusion. Okay, see you then. Bye.
Thank you. Goodbye.
Goodbye.